I guess we should start this, the second tutorial. My name is Eik Jentsch. I'm head of Minerals Technologies GmbH, and together with my colleagues, I'm going to present about Python and SystemC, a dream team for running and analyzing virtual prototypes. I just shortcutted the title a little bit. We split this tutorial in 3 parts. The first part is dealing with virtual platform composition using Python. Basically, that's PySysC. In the second part, we are talking about how to add behavior using Python. This is still PySysC and the newest developments. Last but not least is then about the results analysis using Python, which means how I can use Python to take the simulation results and get meaningful information out of that. Okay, so we start with the VP composition with PySysC. Minerals as a company focuses generally on virtual prototypes for embedded software development and architectural exploration. In architectural exploration, the development often happens in parallel with the hardware development. So it's important to be able to do what-if scenarios for architecture decisions, and the platform definition as such is not fixed because you're working on the platform definition with that. If you focus, if you look at embedded software development, then you have large systems, or sometimes very large systems, where you just want to run subsystems of these large systems to focus on and get reasonable simulation speed for software development. So in both cases, the flexibility in reconfiguration is the key for envisioned model development. And this needs to be addressed somehow. How is this done in a, let's say, classical way? One is using complex configuration systems like reading and interpreting configuration files, let it be XML or JSON based, just passing them and instantiating the design based on them. Or doing code generation based on those configuration files and compile the whole thing and run the whole thing depending on what you want to do. Or the third option would be to use scripting languages as a front end, like Tcl or Python. There are commercial and open source solutions available, which allow integration of different functionality into one prototype, but they are generally limited by the scripting API, which means you need to prepare the stuff to be integrated or to be dealt with using the scripting. Especially if you look at Python. So because we came to the conclusion that Python might be a good option here because it's ubiquitous and well-known, and there are plenty of libraries out there to work with. And so that's why we came to the idea to use Python as a front end for doing structural construction, simulation control, and parameterization, which means we have Python on top and SystemC underneath. But if you look at existing Python integrations like SoCrocket or like, you need to prepare the libraries to be integrated, which means you have to have specific elements to use SystemC from Python, so that Python knows about how to deal with SystemC, for example, or others. Which requires some effort, and that's why you hardly find integrations beyond those core libraries like SystemC, for example, for the SystemC verification library or the configuration and inspection interface. Now, our solution called PySysC, and we talked about that already in several SystemC figures already. The roots come from the Sun. They originally developed some solution, some in-house solution to allow the scientists to use high-performance algorithms with an easy, having an easier accessibility. So they developed a C++ interpreter called Cling. But since most of the scientists do not know about C++, they wrapped it into some Python or Pythonization layer, called it CPPYY, so that you can use those high-performance algorithms from Python without preparing them. We just adopted this approach and developed the PySysC module, on top of CPP-YY, which adds a few abstractions and functions to make working with SystemC more Python-like. This is called the Pythonization. On the right-hand side in the picture, you see how this layering looks like. On the left-hand side, we have Clang and Kling, the C++ interpreter. On the right-hand side, the modeling libraries or the SystemC library, they are wrapped or they are made accessible using CPP-YY, and we have the PySysC layer on top to ease the usage of Python, of SystemC in Python. Now, what are the advantages? There are plenty of libraries available which can be used in Python. For example, NumPy, Skippy, and the like for numerical analysis, which you can then use on the fly while simulating. Also, graphical libraries like GTK, WX widgets, or Qt, where you can build some UI front ends for the VP, for example, let it be the UART or whatever. A very important thing is that due to the use of this Kling and CPP-YY, there's no preparation of the libraries needed, which I'm going to integrate into my design, which means I can use any compiled library having models, for example, and integrate them into my design as long as I have the development header files which describe the content of the library. I can work with this library even without having the source code. There's no source code modification needed. There's no source code annotation needed, nothing. Python or the CPP-YY layer being the base of PySysC allows to introspect variables in the design, which means I can ask the design, what type are you, which is quite handy, for example, for ports and signals. And based on this information, it allows then to dynamically generate or instantiate signals or hook up ports and the like. We will see that later on because we have some longer demo on how to set this up. Since the CPP-YY layer comes with Kling, this C++ interpreter, there's also a JIT coming with the entire solution, which means you can even generate code on the fly for adapters and the like, and do these and instantiate them on the fly based on the particular configuration. So even if things are missing in the libraries or you don't have C++ code for that, you can generate this one and integrate it into your PySysC based design. One important thing here to note is productivity libraries, making things, common elements and infrastructure tasks accessible are very handy here. Examples for such productivity libraries are the greenlib, the SystemC components library, SCC, or the SCML, which are partly open source, partly not open source libraries. But the point is here that those libraries allow to take the effort from the Python part on dealing with this low-level C++ thingy to have some common interface and make the usability easier from Python and the integration easier. Now, this is a long story, which I would like to cut short here a little bit, and we are going to have a look into a practical example. And for that, I prepared some video from one of my colleagues. Hopefully.
Hello, my name is Dr. and I'm a senior software developer. We will build up a Python top level for a small VP system.
Ist nicht?
Based on,
Wait.
processor and the minimal set of derivatives. TGC is meaningless implementation of 30.
Die Frage ist, ob du das.
So this ASS is representing a real. Around this ISS model, we will build up a VP top level in Python and execute a simple hello world firmware. To assemble the test design, besides ISS, we will also use a AON module, core local interrupt controller, router, some memories, and a UART terminal to print messages from the firmware. As usual, we don't want to write the common peripherals from scratch, so we will take a generic router and memories from SCC library. SCC is an open source, lightweight productivity library for SystemC and TLM2. Okay, now let's build a VP top level. In this tutorial, we'll take all the necessary components from the TGC VP repository on GitHub. This is an open source project, and you can easily reproduce all the steps done in this demo session in prepared Gitbot workspace. Gitbot is a web-based development environment where we can edit, build, and execute code. So all you need to reproduce and play with this demo design is basically a web browser and a GitHub account. First of all, let's prepare the environment. Let's update the wheel to ensure we are working with the latest version. In the next step, we have to download and install PySysC. The installation is a little bit tricky. For the PySysC installation, the location of SystemC library must be known. So we have to set SystemC home environment variable. In this environment, SystemC has been installed with Conan. So we can look up SystemC location in Conan built-info file. PySysC needs also to know which C++ standard are we using. So the environment variable stdcx has to match the C++ version of the SystemC build. In this tutorial, we use SystemC library built with C++ 11, so the environment variable must be set to 11. As already mentioned, we are going to use some generic modules from the SCC productivity library. SCC has a Python module for better integration and easier use in PySysC. So let's install it as well. Okay, so that's it for environment preparation. Now we can start implementing the VP top level. We need to import OS path to find C++ headers and libraries. We also need to import logging, for logging, obviously. We import cppyy module, and we import global from cppyy as cpp. And in this way, it will be obvious when we use cpp interface directly in Python. Now we import PySysC and PySysC SCC. From PySysC structural, we'll need module and simulation. Okay, let's set the logging level for the simulation to debug. So now we can load all shared libraries that we are going to use in the simulation. In the first step, let's find out where we are right now. We will use the current location to build the path to the location of the libraries. In this example project, some libraries come from Conan. As you might know, Conan is a C++ package manager. So now we call read config from Conan function with the path to the build directory containing the Conan file. Then PySysC load systemc function is called. This function loads not only systemc, but also further accelerator libraries like SCV and CCI. Now we load the shared objects of the systemc components productivity library. Now design-specific components will be loaded. We start with the instruction set simulator lib, but other libs will be loaded exactly in the same way. For each library, we have to define the include path, and then we load a header file and according shared object file. the huge advantage of the PySystemC approach is that any binary library can be directly integrated. It doesn't require any customization. For example, if a third-party model is to be instantiated, the model can be used directly as it is. It is not necessary to contact the vendor and ask for API customization. It doesn't even have to be a C++ library. It can be C or Rust or D. Only C++ header describing the library interface is necessary. Okay, now all necessary libraries have been loaded. In the next step, we use some convenience functionality from the SCC library to configure the VP simulation. We set log level in C++ to the same level as in Python. We configure SCC to enable trace, which means VP simulation will write SCV and VCD traces. In the next step, we could instantiate our DUT, but we have to create it first. Okay, let's create a structural top level of the system in a separate Python module. Here we have to import again CPVYY and PySystemC. This time we'll also need connection, signal, and clock. Then we create a Python class for the structural top level module. We write an init function, and all design components will be instantiated and wired here. Now we can instantiate components of the system. Let's start with the reset generator. PySystemC module create function is kind of a factory. It takes the class to be instantiated and the instance name and returns an object of a class. In this particular case, it is the RSTGen class in TGFS VP namespace. Now we will instantiate a router as an example of a template class. The template parameter is specified in the square brackets. We instantiate router here with a bus width of 32. So as you see here, we can easily use C++ templates in Python. All other modules are instantiated in the same manner. Okay, all modules are instantiated, and now we can start to connect them. PySystemC provides a clock generator class, which is based on scClock. We create a clock instance here with a clock period of 64.5 nanoseconds and connect this clock to EON interrupt module and to the core. In the next step, we apply a normal signal and wire it immediately from source to sink. What is remarkable here is that no signal type is specified. This is not necessary because the signal class checks the type of the source and the target and creates an according as the signal. This is the Pythonization layer of PySystemC. The type information is no longer necessary, and also syntax is closer to Python than to C++ at this point. In PySystemC, the type information is basically hidden from the user in Python classes. We create kind of a chain here and wire reset to multiple targets within a single command. By the way, we can also wire multiple signals with list comprehension, so one inline for loop. And in the same way, we could instantiate several modules in inline. Now to the sockets. The connection class does for the sockets exactly the same what the signal class does for signals. Here we connect the core initiator socket to the router target socket. Let me just copy paste the rest of the routing wiring. Okay, now everything is connected. The top level hierarchy is now ready and can be instantiated. We import top module from TGC top and create an instance of it. Finally, we have to load the test firmware to prove that the system is actually working. Interesting is here that to load the firmware, we used this elf file property of the ISS core. Basically, elf file is a CCI property. So as you can see, we can configure CCI properties directly from Python. Now we can create a main section and start the simulation from there. The wiring is now complete, but it has not yet taken place until the call of the simulation run function. It was just noted that this wire should be connected to this port and this socket to that socket and so on. But all that can be changed until the simulation run function is called. Okay, now we can actually execute the VP simulation. The firmware is very simple. It basically calculates and prints the factorial of 10. First, we see the copyright from SystemC, and then both Python and SystemC logging. And here we can see the result of this calculation. By the way, in PySystemC, we can easily make use of the SystemC callbacks like end of elaboration, start of simulation, and so on. Let's print, for example, a message from the end of elaboration callback. And here we can see our message from the callback function. Okay, we just created a working VP system top level in Python. In the simulation directory, we will find a VCD and the CV traces. Takes log file is a SystemC verification library transaction recording trace. These trace files can be visualized and analyzed with different tools, for example, with Impulse. And for that, I am handing over to Thomas Haber.
So thank you, Ike. Do you hear me?
Yes.
Okay, video.
Yes, we do.
And you see the screen. Is this okay?
Yes.
Okay, great. Okay. My name is Thomas Haber from 2M, and this part is about simulation results. After the simulation is executed, you find these typical SystemC outputs. There are VCD files, transaction databases, and maybe different kind of log files. You may have additional custom outputs like chord traces, analog waveforms, or custom data with specific information that you generated before. You can use these files to debug your simulator and to extract statistical and functional information. The easiest way to view and analyze these files is within your IDE. The impulse plugin I will use here supports VS Code, like Stanislav used before, Eclipse CIA, both in the browser and desktop variants, and the Eclipse IDE. And it's also capable of building custom web application, but another story. So this output here is the digital simulation. The views are fully customizable. You can select between multiple views. Here on the left side, the signal area, we see all the created signals and scopes. Below there are sortable tables with filters. In the middle, you find all the plots of one specific view. And below, you have one or more synchronized tables and the inspector view to get to the details. I click here to select another view. What you get is the same data, but a different representation. All plots are configurable about their presentation, but also about the input data to show. So you can define scripts or use predefined analysis operations to combine signals or to extract statistical and functional information from these input signals. These scripts can be edited using the IDE editors and presented using one of the existing or custom charts. Next file is the transaction database. You see the transaction and the relations between. Transaction relation can be tracked and followed quite easily. You basically just click on them, and if you want to return, you take the Go Back button. Below you see the transaction in tabular form, and right to it you find all the details. Logs can be of any forms. You may have logs with simple text lines, XML logs, YAML logs, or JSON. Here you find all the configurable readers. You can define configurations for custom log types or use any of the predefined ones. For example, this XML log here. The settings let you define where to find the relevant information in the log file, its format, and how to result into a log sample. There may be output from analog simulation components like this one here. You see here the logarithmic and linear axis. You might have additional real-time traces from one of the cores with task processes and interrupts. Or you may have prepared custom data with statistics. This may be of a custom format or flux trace that supports multiple languages like C, Python, and Java. When there are lots of possibilities to configure such a tool, you need to take care of how to exchange and manage these configurations. The configuration wallet here allows to copy settings from the preferences into the wallet and back. The wallets then can be given to colleagues or customers and can be stored for later use. If you want to try Impulse, you may want to use the Impulse playground. So you see this address at the top line. So basically it's just a GitHub repository with some example files, but inside you find a button to start Gitpod again, like Stanislav used it before. So it starts this IDE in your browser, and then you can play with Impulse if you want to. Below you see the links for the different marketplaces where to find Impulse. Impulse for VS Code is still in an early version. You don't find all the features like in the Eclipse IDE versions like diff and stream data, but it's constantly growing. So thank you.
Okay. Thomas, could you stop your sharing? Great. Okay, this brings us back to the second part, which deals with, again, with PySysC. Here now we are talking, or I'm going to talk about how to add behavior using Python. As I mentioned in the first part, the initial intention of PySysC was to just add, to just have it as a configuration front end to assemble VPs, configure them, and run them. Meanwhile, some work has been done to become able to also describe functionality in Python itself. One thing to note here, for this approach, care should be taken on performance, because there are several layers of software involved, which make it a little bit, well, it takes some time to switch back and forth between Python and SystemC. But on the other hand, it allows to include and use Python libraries in the simulation itself as simulation models, or to visualize on-the-fly simulation results, which means you can build GUIs or simple text UIs. You can create statistics calculations based, I already mentioned it, NumPy, SkiPy, and so on. Or you could even integrate, for example, machine learning or artificial intelligence models like TensorFlow or PyTorch into the simulation and use them as reference models in the simulations. As I already noted, we have here there is some overhead involved if you use threads in SystemC threads in Python, because we have here some kind of a sandwich solution, which means in Python we call the simulation.run, which in turn invokes the SC start module, which then creates the SC thread. In the SC thread, this one, as soon as it's activated, it needs to acquire the global interpreter log of Python. Then it switches to Python and invokes the interpreter, which then does whatever it wants to do. At a certain point there, you will call scwait in Python, because currently only scwait, this model is supported. And scwait then hands back into the SystemC, where the global interpreter log needs to be released, and then the SystemC core wait is going to be invoked, which means there's a lot of code being executed just for switching from SystemC to Python and back to SystemC to implement the simulation semantics. The other thing is that Python as such is primarily an interpreted language, which means it takes time to execute code in Python. Well, if you have third-party libraries which are implemented in C, C++ or like, that's a different story, but Python as such is interpreted, so it takes time to execute the code. So the general advice here is only small or interactive functionality should be implemented in Python itself. The rest you should keep in SystemC. And as soon as you know about the functionality and it's more or less fixed, back to the topic of architectural exploration, you should think about moving the code or transforming the code in the sense that it becomes C++. Now, how does it look like if you use an SC thread in Python? We inherit from SC module. I just go briefly here because I have another live example in a minute. So we inherit of SC module, not of the CPP PySC module. Then we declare the method, or we tell the Pythonization layer what is the SC thread to be called. In this case, it's called the run thread. There's no special change in run thread itself. And within this thread, we can then call the scwait function and pass some sc time. As you see, it's here the plain C++ or the plain CPPYY syntax to call sc time or construct an sc time object, which is pretty clumsy. There's currently work ongoing to make that a little bit more accessible. So, but let's have a look into some practical example. In this example, we are currently at. I need to. So, we are in an Ubuntu session. This is a standard Eclipse IDE using the same project, the TGCVP. As Stanislav already mentioned, this is available in the at GitHub. There's a TGCVP repo in the minres. And there on this PySysc SC thread branch, you will find this example I'm currently showing here. As shown in the slides, we inherit of SC module. As shown by Stanislav in his walkthrough, we just instantiate all the different connections and signals. And here we declare the thread to be, or the function to be called as being a thread. In this case, it's called run thread. And the infrastructure then calls run thread for this particular module. We get some prints, and it does an endless loop, just waiting for a certain period of time and then printing hello from thread XYZ. Now we can execute this one on the command line, similar as Stanislav did. And what we see is the simulation has been invoked with all the debugging. And here we get then intermingled with the SystemC logging output, we get then the callbacks from simulation, start of simulation callback, then the initial one from the run thread itself, and then at certain points in time, I just derive here the actual time from the simulation kernel. I print out at which point in time I am, and the simulation ends. So basically, this can be extended for the sake of simplicity. I kept it in this simple way, just having a simple loop with a wait in there. This can be extended to do much more functionality or call, as I already mentioned, more complex models like PyTorch models or alike. It's also possible to hook up here some GUI. This is another example where we use the same module itself, but we modified the top level a little bit. We use here a PySimple GUI module and put it in a thread. So by adding these 16 lines of code, I set up an GUI, a terminal window where the output is been shown. And if we run this one, you will see same story. The PySystemC initializes, it opens up the window, the simulation runs. PySimple GUI redirects the Python output into this terminal window. So I have a separation. I see in the Eclipse console, I see the output of the SystemC simulation. There are ways to redirect them as well. It's part of the SystemC components library. But for the sake of simplicity, I just wanted to keep it simple. I open here the window, have the console of all the outputs coming from the Python side. So it's a little bit separation. I can, for example, hook up here a terminal, a UART terminal, getting in and output. So interacting with my VP, whatever. Or I can also hook up some statistical analysis so that I can do analysis on the fly. And with this analysis on the fly, I would then hand over to Rocco Jonak, who is going to talk about how to do this analysis, the result analysis using Python.
Short switch of chairs here. So this is the So yeah, exactly. Let me take the next few minutes to talk a little bit about what we can do for performance analysis. I have a few slides here before we go at the end to have hopefully another short little demonstration. Hopefully, I don't need to motivate too much why we need performance analysis. I think today with complex designs, you need more and more. You need some kind of assurance that what you are going to implement will actually meet your performance criteria. You often also want to make architectural trade-off analysis where you want to see maybe in earlier stages of the project, you are not clear about what the architecture should be, and you want to argue about the correct architecture based on some results rather than just in a discussion without having any results available. Also, of course, for software development, the whole question of how to simulate firmware as early as possible, bring it into a design process. That is also becoming more and more an important part of the development. So this performance analysis, so this was why we want to do performance analysis. So what do we need for performance analysis? Now, typically what we are seeing is that you want both textual and graphical analysis capabilities for certain key performance indicators. What these key performance indicators are depends very much on your design, but very often basic performance indicators are things like bandwidth, latency. You do want some graphical components to this analysis because often it is also about visualizing large amounts of data, and I think the human brain is just better often at visualizing things when you see it in a graphical representation. Also, we often have the task of, when it comes to debugging certain details of transactions, you want to have the kind of the classical waveform style analysis. Waveform style, however, based on transactions. And we have already seen there from Thomas a little bit how to use his tool there. And this is basically also here applicable in what I'm talking about now. You nevertheless want also some textual components to your analysis. These textual components, to me, they are often sometimes it is just some performance indicators are very simple to visualize in a simple text file, but also to make analysis more regressible. Right, you have a graphical representation is something that is much more useful in an interactive manner, whereas textual representation is much more useful if you have actually a certain amount of data and you want to make sure that you analyze the results of your simulation in a regression scenario. So we put together actually, so MinRes, we try to bring all the different components that are necessary for such a performance simulation, and we call that TPA, Transaction Performance Profiler. It's actually several components, and we will talk about what that is. But basically, the fun part, the end part that you want to get to is actually to analyze your results, and we see here in a little screenshot a little bit of the a little bit of the actual some graph analysis, also some transaction-based analysis, and often also the interaction with a simulation is part of this transaction performance profiling step. But let's take a look at what are the different components that you need. First of all, you cannot analyze anything if you don't have the necessary input files, the necessary input formats. For these input formats, I mean, you have already heard, I think, a number of different things that are mentioned, especially in Thomas' presentation. I think there are some things that are very intuitive, everybody knows about, for instance, VCD traces. VCD traces, I think almost any simulation, also a transaction level simulation, has a certain amount of signals, for instance, that signify things like the number of outstanding transactions, hit-miss rates in a cache, or also or also buffer fill levels during a simulation. Those are very simple to trace in a VCD format, and we would highly recommend doing that whenever possible. However, for transactions, the situation is a little bit more complicated. Transactions are not that easily visualizable as a VCD trace. So for that, we are using an SCV-based trace format. And this trace format is also, it's very well defined, and in the tool that Thomas has mentioned, you can easily also visualize this type of transaction format. On top, we see also often the need, even though that is a little bit more optional, to get some more information about the design. So this is what I mean here by design information in XML or JSON format. So we do really highly recommend sticking to well-formatted types like XML or JSON. But of course, what you describe in this XML or JSON, this is basically up to you or up to also an IP provider. But we do see the need, or we do see that it helps enormously if you have about your design some what I would call metadata that specifies basically what you design, what you have in your design, what are the kind of properties to look for. And those typically you want to describe additionally in XML or JSON. Of course, you can do also a number of things without this additional information, but this additional information helps you generate more appropriate information. Very important here about this, all these formats is that they generate as much as possible a low simulation overhead, because we are seeing quite frequently one of the biggest issues is that if the generation of data is too big of an overhead on top of your simulation, then it's really not really practical. I mean, it's clear any additional information will generate some overhead. There's not much you can do to absolutely avoid that. But you really, that is one of the key things that we are also providing. Also, some of the components that are part of this SCC, SystemC components, a library that we have already mentioned a few times, they actually help you to generate this data with a low performance overhead. So yes, I think we have already mentioned a little bit about the different formats, so I don't think I need to go into great detail here. VCD, I think VCD is probably the best known format simply from the hardware world. So we don't need to specify too much more there. For additional information, it is very good to have information like an IPExact format. Some companies have RTL files or JSON formats to define more information about the different IPs that you're using. SCV is probably is a very important format from our point of view, because it is for us the best defined open source transaction recording format, and that's why we are using that as the basis. Nevertheless, you have to keep in mind that especially for AT type of simulations where you want to be very cycle accurate, you often need actually additional protocol extensions for real world interfaces like AXI, CHI, and here again the SCC library will help you with predefined extensions. So what I would see as an example system, or something that hopefully I will have still a few minutes time at the end to show some examples of such an analysis, would be maybe a design that could look like this. What we see here is we have a number of traffic generators here, just signified as SCC. So these are components out of the SCC, the SystemC components library. We have here a model of a DRAM from an open source project called Remulator. We have here in the middle a number of different components that are basically routers, different interconnects. They can be non-coherent, they can be coherent, but they basically transport information from initiators to the DRAM. So I think this is a nice little example system that often is used in that format or in a similar format in many projects. So what I would call the performance analysis flow that we are suggesting is basically you start with some kind of a traffic definition. So here we see mainly what we are using at Minros mainly is as a trace format called STL, or a traffic profile format that is defined originally by ARM called ATP. And with these profiles, you can basically drive these traffic generators in your simulation. As I already mentioned, if you have, it helps really to get some additional metadata from the design. Sometimes you also just have the IP itself, but most likely you will have some amount of third-party IPs, maybe also your own IPs that you want to integrate. The integration itself, this is more subject of what I had been talking about. But then we come to the point when we can actually run simulations and analyze the result. And of course, that most likely in a loop, because you want to change maybe the traffic profiles, have maybe also different variations of your design. But all of that is actually, I really want to focus here basically on this last step, on the result analysis. So one component of this result analysis, already mentioned that, is simply, well, I say simply, is a waveform viewing tool, and there we are. We typically use the tool that Thomas has mentioned here. It allows very flexible waveform viewing, both for VCD and for transactions. Of course, for VCD, as you know, there's many options out there. For transactions, it gets a little bit more tricky, but this is, we believe, a good tool that combines the necessary functionalities. So I started with waveform viewing because whenever I talk about VCD and transaction traces, this is the first thing that comes to mind. However, we believe that very often the transaction viewing is very important for debugging, for an interactive kind of analysis. But very quickly, you also get to the point where you want to derive out of this large amount of raw data certain information, statistical information, also like the bandwidth, latencies in terms of average, min, max, the fill level of your buffers during the simulation. So for that, typically you want to have a post-processing step. This post-processing step typically also needs some knowledge about the protocol-specific extensions that you're using. That's why I want to point out here again that in the SystemC library, you have actually extensions to the generic payload that are specific to the current set of AMBA protocols. So the idea then is after my simulation, the output goes first through a post-processing step. And out of this post-processing step, we get then a number of files that have what I would call more condensed information. So what can you do with this more condensed information? One thing that we really more and more see in the industry is that people are using dashboards. The term dashboard is actually not specific to SoC design. Dashboards are used all over in the industry. They are used in financial context, insurances using dashboards, medical industry. So they are very useful. So what do I mean by dashboards? A dashboard would be a presentation where typically a backend runs on some server and provides a web-based interface to a client. So the client would be your web browser that you view locally, but the actual information runs on some backend server. Could be in the cloud somewhere, could be your own local cloud servers, could be also your virtual machine, but whatever is needed there to derive the information. The dashboard then, of course, allows you to filter out the relevant information. Very often these dashboards are configurable. And they allow a really, typically a really nice representation of your data. So now this is the generic way, how dashboards, how the term dashboard comes into play. We have adopted mainly an environment called Dash. So now we finally come also where Python comes again into the play, into the picture here, because Dash comes as one of the bindings comes with a Python binding, and this is typically what we would be using for data analysis. So you can take this data that comes out of our performance analysis scripts, which took in this raw data and generated some more condensed data. And you can use Dash to generate some dashboards for yourself. This is a very easy mechanism. So Dash provides easy Python bindings that allow you to generate actually your own dashboards. And so what I want to show here at the very end, last few minutes,
Moment. Nee.
1 second. I think is this one, no?
Nee, das war eigentlich der guck mal hier oben.
Ja,
nee, der.
Okay, yeah. There we go. Sorry about the little hesitation there. We just needed to find where the right setup is. Yeah, let's go first to this dashboard here. So what I'm showing here is actually 2 examples for dashboards that I have prepared. This dashboard here analyzes, first of all, in this tab, the bandwidth of different interfaces in my simulation. So these different interfaces are AXI interfaces. Here I have a CHI interface. And I ran actually on this design different scenarios with different traffic patterns. So I don't want to go here into details on what these traffic patterns are, but I just want to point out that this environment basically allows you then to very easily visualize the results of this simulation, key performance indicators, like here the bandwidth over these different interfaces. In another tab, I have the latencies over these different interfaces, and you can compare here basically the different bars signify the results of the different scenarios. So I can, for instance, here take also, if I want to focus just on individual scenarios, I can filter out here some of the scenarios that are shown, and I can nicely, very quickly see how the different traffic pattern then result in different resulting latencies and bandwidth on my design. I can also do some visualization over time. So here I'm plotting over time, basically just for one scenario for the different interfaces, the number of pending transactions. So if we zoom in here a little bit, you see something that very typically happens, right? If you start to fill up an interface, the number of outstanding transactions rises to a certain point. This point is either defined by a limit in your design of the number of outstanding transactions, or maybe that this is now the time when the first results are coming back and you go into kind of a stable state. So you can very nicely see here these common effects. I can go to the main scale. I can also use this environment to even visualize the raw data. Sometimes, as I said, sometimes it's simpler to just look at the raw data, or to really make sure that the visualization actually has taken the raw data correctly into account. So I can here have basically an Excel-like visualization, and I can also both change the order of the information as well as filter different parts of the information. So this is, I hope, shows how you can use such a dashboard efficiently. And as a last part, I just wanted to, the text editor.
It's closed.
It's closed.
Ja. Ich weiß nicht, wo es hin ist. Das ist das Problem. Da musst du hier drin.
Das war,
ja. Dann hier SF Media, SF Downloads. Und da müsste irgendwo
ja, hier oben. Okay.
Öffnen.
Ja, So as the really the very last part, because we are running out of time, I just wanted to show the script, the dash script that I used to generate this dashboard. And without really wanting to go into a great detail, let me just scroll down through this this Python script here, and you will see that it's actually to me at least, a remarkably low number of lines that I needed here, 175 lines of code to do all of this analysis. Of course, the main, I would say, the strength of Dash is that it hides basically the main working functions, of course, in functionality that is hidden in libraries which you import. We have seen that already also in Stanislav's demonstration, where we have to import here a number of components from Dash, which are doing the heavy lifting here, but it allows me to focus on the performance analysis on some relatively easy scripting. And we believe this is really a very efficient way to analyze your results. So I think with that, I'm also done with.
And over time.
And over time.
Okay, I started to answer already some questions in the chat. If there are further questions, since we are now already 3 minutes over, yeah, it's lunch break. So from that perspective, I hope it doesn't matter too much. If there are further questions, just get in touch with us either via the GitHub issue tracker on SystemC or via emails, which is part of the which is shown in the conference schedule. So we are happy to answer questions and help in getting SystemC distributed. One thing to note here is what we showed in the first and the second part is currently not yet as pull request in the official Accelera repository. So at the moment, I would recommend to use our repository if you want to play with that. The other thing is playing is easy with, or an easy start with the gitpod.io. The link is in the TGCVP repo. So from that perspective, it should get you going. There's also some setup script in a part of this repository in the SystemC subdirectory, where you can easily install all the needed modules so that you get the SystemC up and running within a few minutes. I just see a question about commercial simulators. Well, that's a fairly good question. Yes and no. Yes, it should. No, we never tested it. So basically, at the moment, it doesn't work.
Well, so I would say there's several parts to that, right? Because we have shown here several different components. The SCC library, we have compiled it against some of the commercial simulators. Not all of them, but we are planning to make sure that the SCC library is really compatible and runnable with all the commercial providers. As far as actually, especially the dashboarding is concerned, basically once you generate the files, it doesn't really matter if you do it in the context of a commercial simulator or as part of an OSCE simulation. But as I pointed out, we are focusing really on a flow for now that involves the OSCE simulator. It's clearly the intention that using a commercial simulator would also be possible, but it is not fully tested yet in all aspects.
Okay, so now we are 6 minutes over time. I thanks for your attention and your time, even staying with us for longer. And as I already said, don't hesitate to get in touch with us if you have any further questions. Let it be about Impulse with Thomas or about the dashboarding and post-processing analysis or the SystemC, we will be happy to get in discussion and maybe bug reports, code contributions, whatever. Enjoy your day, enjoy the conference, and goodbye. Oh. Ja, die Session ist gekillt.
Ah, okay.